a magnetic dipole or a bar magnet in magnetic field. What do you mean by potential energy? Potential energy is the energy stored in a body in a particular position, right? If a bar magnet is in a position, then that bar magnet on that position, to place on that position, if some work has to be done, then that work is stored as potential energy, and that will be the potential energy of the magnet. Clear? Work done to rotate a magnet or work done to rotate a magnetic dipole in a uniform magnetic field is stored as the potential energy of the magnetic needle or magnetic dipole. Let us see. Here is a uniform magnetic field of strength B, and this is a magnetic dipole or bar magnet of magnetic dipole moment M, and this M makes an angle theta with the magnetic field, right? This is, let us say, this is the initial position. Now, if we want to rotate this magnetic dipole or bar magnet by a very small angle d theta, then I have to do some work, because at this position, when the magnetic dipole moment makes an angle theta with the magnetic field, the magnet experiences a torque, or a torque is acting on this bar magnet, and that torque is mb sin theta. We have already done this. mb sin theta, amount of torque is acting on this dipole and which tries to align the magnet along the magnetic field. Now I want to rotate this magnet opposite to this torque by a very small amount d theta. So I have to apply this amount of torque against this torque, against the torque acting on the dipole due to the magnetic field. That means I have to externally apply this amount of torque to rotate this magnetic dipole by a small angle d theta, right? So I have to do some work, and the amount of work to be done to rotate the magnetic dipole is equal to tau external into d theta, and external tau which I have to apply will be equal to the torque acting on the dipole due to the magnetic field. Then this will be the work done to rotate the magnet from theta to theta plus d theta. Now total work done to rotate the dipole from one position to the another position, that is from, let us say, angle theta 1 to theta 2, will be equal to W equals to integration dW theta 1 to theta 2, and that will be equal to theta 1 to theta 2 mb sin theta d theta, or we can write mb integration of sin theta is minus cos theta, integration limit is theta 1 to theta 2, or from here you can write minus mb into cos of theta 2 minus cos of theta 1. This is the amount of work to be done, and this amount of work is stored as potential energy. Now the potential energy of the dipole is equal to U equals to this W is equal to minus mb cos of theta 2 minus cos of theta 1. Rather, you can say this as the potential energy change, right? Potential energy change from one position to another position. Clear? Now if we assume that at theta equals to theta 2 equals to 90 degree. If we assume theta 2 is equal to 90 degree and rather we can say theta 1 equals to 90 degree and theta 2 equals to theta. Then what happens? Then you get u is equal to minus mb cos of theta 2, that means cos of theta, and minus cos of theta 1, that is 90 degree, and cos 90 is equal to 0. You get minus mb cos theta. That means if we start our rotation or initial position, theta 1 is equal to 90 degree, theta 1 is the initial position. If the initial position of the magnetic needle or magnetic dipole or the bar magnet is perpendicular to the magnetic field, initial position, what does this mean? This means this is the magnetic field and initial position is this. This is the magnetic dipole. This angle is theta 1 is equal to 90 degree and we bring here. This is theta. This is the final position, right? Then this is the potential energy and which can be written as minus m dot b. M dot b minus m dot b is the potential energy of a dipole or of a bar magnet in uniform magnetic field. Now we get u is equal to minus m dot b, that means minus mb cos theta, right? Now if theta equals to 90 degree, what do you get? Theta equals to 90 degree means when it is perpendicular. When it is perpendicular, right? When it is perpendicular to the magnetic field, you get u equals to cos 90 is 0. Right? You get u is equal to 0. That means we assume that when a magnet, bar magnet, is perpendicular to a magnetic field, its potential energy is 0. Please, clear? That is the reference level. As we assume that on the surface of the earth potential energy is 0. Similarly, we assume that when a magnet is perpendicular to a magnetic field, its potential energy is 0. Right? Now, if theta equals to 0, then you get u equals to minus mb cos of 0, which is minus mb, and if theta equals to 180 degree, you get u equals to minus mb cos of 180 degree, which is minus 1, that means plus mb. See here, this is minimum. This is minimum potential energy and this is maximum potential energy. That means if bar magnet is anti-parallel to the magnetic field, then its potential energy is maximum and which is unstable equilibrium. And when theta equals to 0, its potential energy is minimum, it is the stable equilibrium. We know that if a body is at minimum potential energy, its equilibrium is stable, and if its potential energy is maximum, its equilibrium is unstable. Like that. If a bar magnet is perpendicular, its potential energy is 0. If it is anti-parallel, then its potential is maximum, then its equilibrium is unstable. If it is along the magnetic field, then its potential energy is minimum. We can say this equilibrium is stable equilibrium.